Transconductance, GM, is a key parameter in electronic devices, particularly in MOSFETs and bipolar transistors. It represents the change in output current, drain or collector current, per unit change in input voltage, gate or base voltage. The unit of transconductance is Siemens, S. In MOSFETs, a higher GM value implies greater amplification and improved linearity, making them suitable for applications like audio amplifiers and RF circuits. For bipolar transistors, transconductance is the ratio of the change in collector current to the change in base voltage. It indicates the device's gain or amplification capability. Factors affecting transconductance include temperature, doping concentration, and device geometry. Transconductance, GM, is the change in drain current, ID, per unit change in gate source voltage, VGS, with the drain source voltage, VDS, constant. It is the slope of the transfer characteristic curve, indicating the device's amplification capability. The unit of GM is Siemens, S. Source. The source is one of the terminals of a MOSFET where current enters the device. It is responsible for providing the charge carriers, electrons or holes, that flow through the channel to the drain terminal. 2. Drain. The drain is the other terminal of a MOSFET where current exits the device. It collects the charge carriers that have passed through the channel from the source terminal. 2. Channel. The channel is the region between the source and drain terminals in a MOSFET where the current flows. By applying a voltage to the gate terminal, the channel's conductivity can be controlled, allowing or restricting the flow of current between the source and drain terminals. 2. This curve illustrates how the drain current changes concerning the gate source voltage, providing insights into the device's behavior and amplification capability. In the curve, as the gate source voltage, VGS, approaches zero, the drain current increases more rapidly, indicating the effectiveness of the gate voltage in controlling the current flow between the drain and source terminal. The transconductance curve is nonlinear, showing that changes in VGS do not directly result in proportional changes in drain current, highlighting the complex relationship between the input voltage and output current in these devices. Different regions on the curve, such as the cutoff region, ohmic region, saturation region, and breakdown region, represent distinct operating conditions of the transistor, providing valuable information for circuit design and analysis. Transconductance, GM, in a bipolar junction transistor, BJT, is the ratio of the collector current, IC, to the thermal voltage, VT. The formula for calculating GM in a BJT is GM equals IC/VT, where IC is the DC collector current at the Q point and VT is the thermal voltage, typically around 26 MV at room temperature. The transconductance of a BJT is not independent of device size and shape, as it is proportional to the collector current and can vary widely, typically falling within the range of 1 to 400 millisiemens. The transconductance is a fundamental quantity in BJT design calculations and plays a significant role in determining the gain and performance of the transistor.